Okay, so we're going to change gears a little bit and feature the metal. So more of an inorganic approach in what I thought I would talk to you about today. Basically, it deals with studying the reactions of late transition metal complexes with molecular oxygen. So really what my group spends a lot of time on is studying reaction mechanisms, and the goal behind that is really to impact homogeneous catalysis. And so this kind of strategy, as you know, as we saw in Jean-Claude Mew's talk, with looking at the individual steps of those 4 catalytic cycles he had based on the different oxidation states. So those individual steps that make up those catalytic cycles are so important to understand in terms of optimizing and developing new catalysts. And our particular goal is to develop new catalysts for oxidation reactions. And those include oxidations of saturated hydrocarbons, so that gets into the CH bond there. So in particular, we're interested in aerobic oxidation. So using oxygen. This is really because it's environmentally benign, it's inexpensive, it's abundantly available. So it's really the ideal oxidant. And moreover, it's really the oxidant of choice for industrial oxidations. And so when you look at this list here of base organic chemicals produced by means of oxidation, you can see for the most part, these oxidations are done with air or oxygen. However, there are some exceptions in this list. And so propylene oxide is the 5th largest chemical produced by oxidation, here, organic chemical. And what you can see there is currently you can't use air or oxygen, even though you can here for ethylene oxide. Similarly, we can't currently make adipic acid on scale using oxygen, and nitric acid is used. So we wanted to ask the question, how do we activate and incorporate oxygen into selective homogeneous catalysis so that we can do oxidations, for example, like propylene, instead of using these more expensive or more hazardous oxidants. And then can we do, for example, reactions like cyclohexane to adipic acid with oxygen? Moreover, we're interested in reactions that don't even show up on that list because we can't do them yet. So this would be, for example, oxidation of alkanes to alcohols. So, for example, for a longer chain alkane, alcohol, this would be instead of going through a multi-step process involving cracking it to get to the olefin and then hydroformylation and hydrogenation to get to the alcohol. Or you could even ask for short chain alkanes. There's so much shale gas available, methane. How can we do direct partial oxidation of methane? This is a critical problem because it's really expensive and hazardous to transport methane. And the cost, if you have to use if you have to condense it to do liquefied natural gas or running these very thick pipelines because you're running gas through, and these are much more expensive than oil pipelines. What happens then is there's a great deal of natural gas that's what's called stranded. So when it comes out of the ground and you don't have a way to transport it or use it directly, your only choices are really to flare it, to just let it escape, or to pump it back into the ground. So pumping it back into the ground is expensive and it sometimes hurts your oil production. Ignoring it means methane is a worse greenhouse gas than CO2, so what happens is it's flared, and that's shown here. Many people have seen this satellite view of flaring. This is the upper Midwest in the United States, and you can see people with their lights on in Denver and Minneapolis and Chicago. And this is North Dakota up here, the Bakken oil field. So while many people have seen this picture and seen how dramatic the flaring is in North Dakota, I think what's important to realize is this isn't isolated to North Dakota. This is a worldwide problem. So we're flaring methane gas at all these sites all around the world. That's a tremendous waste. So the question is, could you convert that methane gas to a liquid or something that you could move? And along those lines then, the current technology, we actually do convert methane to methanol, but the current technology is to do that going through syngas. So you need $1 billion plant like shown here, and you take methane and you steam reform it at very high temperatures to form CO and H2, and that's uphill by about 50 kcals. And then you take CO and H2 together again over a different catalyst here, and that's downhill by 21 to make methanol. Okay, so you've lost 30 kcals in the process, but, and this was great technology when it was first developed, but when you stop and think about it, if you could design how to convert methane to methanol, would you go through and decide to break every CH bond in the molecule and then put them back together? Right? It doesn't seem very efficient. Instead, what you'd like to be able to do is simply break that one CH bond, insert oxygen, and get to methanol. This would be now an atom-efficient reaction, downhill by 30 kcals. You'd be in a very good position. And there's evidence then that you might be able to do this on a commercial scale with transition metal catalysts. And so that has to deal with CH activation. And so you can see we can draw these potential cycles for doing this. So you can see in this first case we'd have CH oxidative addition of methane to form this methyl hydride compound, and then we can imagine oxygen insertion to form this methyl hydroxide, and then a CO reductive elimination in the last step. And so there's been a lot of work by many investigators on adding these CH bonds, in this case shown as an oxidative addition type reaction, reductive elimination of CO bonds. You can also imagine inserting oxygen into the metal carbon bond and then having a OH reductive elimination in the last step. Similarly, we can think about olefin epoxidation reactions by inserting oxygen into a metal hydride bond to form this metal hydroperoxide, and then transferring the oxygen to the olefin, and then doing a hydrogenolysis reaction with hydrogen of the metal hydroxide back to the hydride. You can also think about alkane dehydrogenation, run instead of at through high temperature reactions, running this at low temperature by using oxygen as your hydrogen acceptor. So you can think about doing CH activation to form this metal alkyl hydride, beta hydride elimination, and then oxygen back to form your low valent metals. So why is this so hard to do? Well, it turns out that these reactions in black, there's been a lot of studies. So a lot of people looking at oxidative addition of CH bonds, CH activation in general, reductive elimination reactions. These reactions in red and blue really haven't gotten the attention of the community. And this is because most organometallic chemists work in glove boxes and Schlenk lines and vacuum lines, and they avoid oxygen at all costs. And the problem with that is that leaves us in a bind because we don't really know how oxygen reacts with these compounds. And so really to use oxygen as a reagent across many reactions, we need to understand how oxygen reacts with metal hydrides, with metal alkyl hydrides, with metal alkyls, with open site metal complexes. And the key in this is that we really need the fundamental science to understand this at the same level that we understand, for example, how CO inserts into a metal alkyl bond, or how an olefin inserts into a metal hydride or a metal alkyl. We need that kind of fundamental knowledge. And so we can start with, my group has really been thinking about all of these types of species, but if we start out with metal hydrides, so metal hydrides can react with oxygen to form these metal hydroperoxide species. Sometimes it stops at the metal hydroperoxide species and you can isolate it, and sometimes they go on further to reduce the oxygen. But typically the first step is this insertion of oxygen. And we can ask then, what are the mechanisms of this reaction? Well, a while back, Doug Wick, who was a former postdoc in the group, looked at this chemistry as shown here, where we had this platinum-4 complex, this platinum-4 hydride that inserts oxygen to form this hydroperoxide species. And you can see you can isolate that. So it's a very well-behaved reaction that then we could look at the mechanism. And we were particularly interested in looking at the mechanism of this reaction because these types of dialkyl hydrides with a TP, a tris-perazyl borate ligand, these types of complexes could be formed by CH activation so that we could activate, in this case, pentane to form the N-pentyl derivative, or cyclohexane to form the cyclohexyl hydride. And so we're saying that these types of dialkyl hydrides can react with oxygen to form the hydroperoxide. So that's 2 steps of the cycle we would need. So Jen Look was a graduate student who joined this project and did some beautiful investigations on the mechanism. What happens is when you add oxygen to these reactions, you form the hydroperoxide product mostly with a small amount of this hydroxide, and the reaction profiles look like as shown here. You can get these reproducible reaction profiles when you do the reactions in the presence of a radical initiator, in this case AIBN. And what you find is that they have this sigmoidal shape. That's typically characteristic of an autocatalytic reaction where some of the product or an intermediate catalyzes the reaction. That leads you to a two-term rate law for this reaction. And really what we found in this case is that we have a radical chain reaction. There's no dependence on oxygen. You can see here 5 or 10 atmospheres. We can find this empirical rate law as shown here. What we found through these studies is really that these reactions are very similar in many ways to organic oxidation. So I wrote this out now here as R. So this is just typical organic oxidation, but now we're saying that R is equal to this metal fragment, so everything but the hydride. And so you have an initiation routine where you would generate your, in this case, instead of being an alkyl radical, this is a platinum 3 radical. That reacts with oxygen to form the peroxyl radical, and then that peroxyl radical abstracts a hydrogen from another platinum, as shown here, to form the hydroperoxide product. And then its termination down here. There's an auto-acceleration step, which turns out that actually the product here can react with initiator to generate another radical chain here. Okay, so we had a good grasp on the mechanism of this reaction. We wanted to know how general was this. So around that time, we also found this reaction mode, palladium-2 hydride plus oxygen, to generate this palladium-2 hydroperoxide. And we were curious then, is this going to go by similarly by a radical chain pathway? In fact, we saw similar products that we see mostly the hydroperoxide and a small amount of the hydroxide. But in this case, we found that there was actually no inhibition by inhibitors, radical inhibitors. The rate was not affected by light. We could get very reproducible rates. These are first order reactions. And we also see a first order dependence on the oxygen. So second order overall, and with respect to first order in the palladium, first order in oxygen. We also see a significant kinetic isotope effect of almost 6 for the pH versus PD, palladium hydride versus palladium deuteride. This led us to consider, well, first of all, it doesn't have any signs of being a radical chain type pathway. So that left us with a couple of options. One is that because it was a square planar species, it has an open site. It's possible that oxygen could enter that open site as shown here. And then we could have migration of the hydride to the oxygen. So this insertion step here would have to be the rate determining step in order to see that isotope effect. Or we could have oxygen react directly with the hydrogen and insert that way. We couldn't really distinguish these based on our experimental results, so we turned to computations in collaboration with the Goddard group and the Mueller group then at Sandia and Rick Kemp's group there. And so what they found, first of all, was there's no interaction of oxygen with the open site of the palladium. And furthermore, what appears to happen is that oxygen approaches the hydrogen and abstracts the hydrogen atom. It flips around, you go over the triplet to singlet surface down to the palladium hydroperoxide. So this is referred to then as a hydrogen atom abstraction mechanism. Furthermore, we can look at other complexes. These were all looked at computationally, and we found that the longer these bonds are, the lower the barrier for the hydrogen atom abstraction, or HAA. Around this time, Shannon Stahl's group was looking at a very similar reaction. So this is a palladium-2 hydride plus oxygen going to the hydroperoxide. So that on the face, it looks very similar. However, he found a very different mechanism, and that is that it's reductive elimination down to palladium-0, and then interaction to form a peroxo, palladium-2 peroxose species, and then protonation to form the palladium-2 hydroperoxide product. In very interesting investigations, Shannon's group also found that there was a crossover between his reductive elimination mechanism and the hydrogen atom abstraction mechanism that we had observed. And that as he did a Hammett study here with electron withdrawing groups, you are more towards the reductive elimination. As you move towards more electron donating groups, which then would presumably have a trans effect to weaken this bond, you go towards a hydrogen atom abstraction type thing. Still one more mechanism has been seen now for gold hydrides. So this is Bachman's system and then studied by Harvey, which found they considered these various different mechanisms, but settled on this third one, which involved an oxidative addition, to form the gold-3, and then migration to the peroxo to form the product in a recombination step. Okay, then, so really what we have is that it's not quite as simple as the mechanism, for example, for an olefin or a CO insertion, where all the metals seem to follow a very similar mechanism. We're finding very different reaction pathways here, but what's comforting is that there have been now various examples from different groups. So from Nocera's group and Rausch's group, where we see some of the same types of patterns, whether they're a hydrogen atom abstraction mechanism or this reductive elimination mechanism. So these general mechanisms of reactions are beginning to emerge in this. And as I mentioned, you don't always get to this hydroperoxide species. Sometimes this goes on further to total reduction of the oxygen. That's something we saw in this reaction here. So this is a reaction that Kate Allen discovered, where she had this iridium hydride, which reacts in air to form the bis-acetate, air with acetic acid present to form the bis-acetate complex. And this goes in very good yield. We're excited about this because this compound here activates CH bonds. And so in some earlier studies, we had found that this bis-acetate complex can react with benzene to form the phenyl compound as shown here at 100 degrees. More exciting in terms of alkane dehydride, in terms of CH activation, is that it could also do alkanes. So shown here is N-octane. Nishiyama found that at 160 degrees, this would undergo formation of this octyl complex. And then furthermore, we found that when you didn't have a base present, but simply heated it hotter, so this is shown at 200 degrees, you would actually eliminate the octene and form this hydride. So if we put those two steps together in terms of doing the beta hydride elimination, and now remember, this is the hydride complex that reacts with oxygen, what you find is you actually have a potential cycle to do alkane dehydrogenation with oxygen as the oxidant. So we have the bis-acetate complex, which activates the CH bond to form the octyl, and then we have beta hydride elimination to form the hydride, and then we have oxygen interaction to form the bis-acetate complex again. Now, unfortunately, this looks very nice on paper like a catalytic cycle, but it doesn't work in practice. And the reason being that these reactions are at wildly different conditions. So if this oxidation happens at 25 degrees, the CH activation is 160, the beta hydride elimination is at 200. So we set apart, and this is work that was carried out in Sensi, working as a team to really think about how we could get these all more on the same page and to a lower temperature. The problem being that at these high temperatures, the oxygen can do a lot of other things, and they can do some non-selective reactions rather than just the reactions we want. So through this process, the Jones group found that they could lower the energy of this beta hydride elimination by changing the carboxylate group. In some very exciting work, Goldman's group found that with Lewis acids, they could get this beta hydride elimination down from 200 to 55 degrees. So now the key step seems to be lowering this. And interestingly enough, Kelly Kim, who you just heard about in Brian's talk, has been working on that project along with Sophie Rubashkin and here at Penn. And they found some interesting compounds that can lower the energy of that reaction. I did want to talk about one more topic, and that's the oxygen insertion into metal alkyl bonds. This has actually very little precedent with late metals. You can count the number of examples basically on one hand. But late metals are very well known to activate primary CH bonds. So we set out to find out, was it possible that we could observe this reaction of oxygen insertion? And if we could observe it, how does the reaction proceed? Well, we were pretty surprised when one of the first complexes we looked at, which is this generic square planar palladium-2 compound, so this is bippy palladium dimethyl, this inserts oxygen to go to the peroxymethyl compound. Luc Boisvert, who's now at University of Puget Sound, did some beautiful work as postdoc on the mechanism of this reaction. We found that the rates were highly variable. The reactions were faster and light, dark, all kind of the hallmarks for a radical chain process, including he was able to work out the rate law for this reaction, again, in the presence of AIBN. This, again, follows a radical chain type process with initiation, propagation, and termination. And the key in all of this really is the fact that the propagation takes place as shown here. That is, rather than an abstraction mechanism, which worked for hydrogen, but it's hard to abstract a whole methyl group, what happens instead is this peroxymethyl group adds to the palladium-2 center. So you do an associative substitution to form this 5-coordinate palladium-3 intermediate, and then this kicks off methyl dot, which reacts more with oxygen to go back to your radical chain carrier, and this goes around and again and again. And this platinum-3 intermediate actually also participates in the termination step. So that gives you the rate law shown here. A similar mechanism was proposed in some work by Kyle Grice, who looked at oxygen insertion again into a square planar, in this case platinum complex. Oxygen insertion happens trans to the weaker weaker platinum methyl bond, which would be trans to the stronger trans director there. So the results here again are consistent with a radical chain substitution. One more example is this one by Bertovcik, where they found that this was a photochemical reaction, which was oxygen insertion to generate this peroxymethyl. They found quite a different mechanism, which is shown here. Their most recent proposed mechanism is based on this computational work, where you photolyze it to an excited state species here that reacts with oxygen, and then, depending on what these R substituents are, can either undergo the methyl migration this way or down this way. We were interested again in finding out how general are these reactions. We decided to look at this palladium-2 compound as shown here with this PNP type ligand. The reason being the methyl group was trans to a pyridine, as it was in the terpy examples of Bertovcik or in our BIPI example. They're cationic and tridentate like the Bertovcik example. Karina Smol worked on this project, and what she found was that there's actually no reaction with oxygen. When she put AIBN in, we only observed decomposition of the AIBN, but again, no reaction. So she tried the photolysis that had worked for the Bertovcik system, and in this case, what she found was not the peroxymethyl, but she got this PNP chloride and also this complex here where we oxidized off one of the phosphine groups. So to try to figure out what was going on in this case, she did a control reaction without adding oxygen. And under these conditions, what's important is that she saw this compound here with a de-aromatized ligand. So this is similar to these PNP ligands, very popular, popularized by the Milstein group. And so you can get this de-aromatized type structure. This, in our experience, when you have a negative charge where you can have a resonance structure to put a negative charge at a site like this, can often lead to oxidation. And in fact, if we take that de-aromatized complex, react that with oxygen, you see exactly that oxidation of the ligand that we saw. So we wanted to, again, know what's going on in these reactions. All of our results are consistent with the mechanism as shown here, that the photolysis leads to palladium methyl bond cleavage, homolytic cleavage. If you don't have oxygen present, that methyl group can abstract a hydrogen atom from the backbone, then to form this product. We can also trap out the methyl group with tempo. If you do have oxygen present, you can form the methyl peroxo species, which can then go on, in this case, to form the methoxy radical, which can again abstract the hydrogen from the backbone, form the de-aromatized species, and again, oxidize the backbone. So clearly you have to be worried about the ligand set you put on the metal, even if they don't look like they're going to react. These types of reactions can happen. So we move towards this PCP type arrangement as shown here. And what we found in this case, again, under photolytic conditions, oxygen reacts, and now we completely oxidize the methyl group to form this bicarbonate group. Again, the mechanism proceeds. I'm not going to go through all our results on this. We did some C13 labeling studies because we also see methanol produced with C13 labeling. You can see there's also some C13CO produced. Basically, what's happening again is photolysis leads to the methyl carbon bond cleavage. We can test that with tempo again, and you can just look up all the organic reactions of what those radicals can do under these conditions to eventually oxidize here to methanol and then formaldehyde, which can then go under further oxidation. So in both of these cases, what we're really experiencing, if we just ignore this backbone for a moment, these photolysis reactions are leading to this palladium-carbon bond cleavage. And that's then not getting us down the pathway that we were interested in going, which is as shown here. We're interested in seeing whether we can see this type of associative substitution at the platinum or palladium center. And so these are the ones we saw, the associative substitution, radical substitution reactions. We're not seeing it with this PCP type methyl group. So what's the difference? Well, we thought about the fact that if we have to do this associative reaction, what happens is these T-butyl groups on the phosphorus are really going to prevent this type of an associative process. And if that's correct, really all we need to do is think about more flat ligand sets to get these type of reactions. And in fact, that's exactly what Hannah has done here, where she's looked at these BPI type ligands. So these are very flat ligands where you can find that you can add oxygen and very nicely undergo clean reaction to form these methyl peroxo species. Again, faster and light, and with AIBN, they're inhibited with added BHT. And she did some beautiful kinetics on these systems. Again, found a rate law really analogous to that we had observed with original BIPI palladium dimethyl system. So all these data are consistent again with that same type of a radical substitution mechanism going through the palladium group. So if I just summarize, as I said, it's not as clean as a CO insertion mechanism where we see methyl migration, a site opens up, new ligand comes in. We're seeing a variety of different mechanisms, but it is comforting then that we're finding multiple examples of all of these different types of mechanisms. But that all said, I'd say we're still very early on in this whole process. For example, in these alkyl systems, we now have a total of 5. So we should be expecting more mechanisms. Hopefully the further ones will fit into these lines. But I think this is a really rich area to really understand the reactivity of organometallic compounds with oxygen, because we're going to need that if we want to put together cycles that use oxygen. And if you want to do something on a large commercial scale, so for example, like methane oxidation or any of these large commercial commodity scale reactions, you're going to need to use oxygen as an oxidant. So with that, I just want to thank all the people who have been involved in this work and the various funding institutions. All of this started at the University of Washington, where we had our Center for Enabling New Technologies, and part of this work is supported by that. We recently moved to Penn. This is the team at Penn, including Ben here. And now we're working on some of this chemistry through the Vagelos Institute for Energy Science and Technology. And so I want to thank you all for listening, and also thanks to CCHF for the opportunity to present today. Thank you.